that genetic algorithm. What happens that in case of a parabolic nature, we have the like a linear nature of a curve. Last day, when we have multiplied the value of SOC or DOD, that the DOD we had taken into consideration, we were multiplying it with the drop. That's what was happening across the terminals from the OCV to the terminal voltage. And that's what the linear relation was there in the lead acid domain. But once it is related to the lead acid, so that's not the linear relation we have, right? Like just for an example, if I say that this is the actually open circuit voltage, if you have to gather in case of a lead acid, which is a polynomial nature. So this is the formula, that's what we follow, where Kn into the SOC, whatever is, up to the value to the power n, and that it keeps subsequently going on up to the K naught would be your minimal cutoff value, like the cell cutoff value you want to fix it like a 2.7 or 2.8, whatever the practical value comes to you. So the K naught would be the last one. So actually it is that K1 into SOC to the power 1 plus K naught into SOC to the power 0. So SOC to the power 0 will make it 1. So that's why we at the end we add the value as a 2.7 or 2.8 for the purpose of a lithium ion. If it is like a nickel based cells, so there we need to add the value like 1.2 or 1.3, because that's the minimal cutoff value for the nickel based cells are considered. So I was talking about the algorithm. So what the thing is, like any of a cell, lithium cell. So this is these are the some of the data points we have respective to the open circuit voltage with the SOC, if it is. So for one cell, these are the data points. Whenever we are going to do the modeling, so we need the accurate data points, and these data points are after of a either of a charge cycle you will be taking the data points, or of the discharge cycles you will be taking the data point. But once you have to estimate the things, so you do the modeling on a standard basis, not specific to the charge cycle based or not specific to the discharge cycle based. If the aging or something, or like the battery pack is aging, so there the relation, if you are doing with the open circuit voltage with the SOC, so there the multiple of a charge and discharge cycles are happening. So exactly of a either respective to the charge cycle based or only respective to the discharge cycle based modeling will not be successful. So what we need to do, that we need to take an average value out of it, and based on which we do the modeling. So this is the relationship data between of our open circuit voltage and the SOC. So like 4.16, it is the fully charged, that's the 100% SOC. And as the open circuit voltage is depleting down, we have the depleting SOCs, as you can see. So approximately of a 50% SOC comes 50 to 55, 50 to 60% of a SOC comes at a 3.7 or 3.8. If you remember that I told you multiple of a times that once we are doing any kind of a test, so we do a complete of a charge cycle, then we do the discharging of the cells, and then we bring the cells up to the 50 to 60% of a SOC. And that's why this value is 3.7 to 3.8 volts is the SOC around of a 50 to 60%. So this is the graph is. But
so is this a nominal voltage then in that case?
Which one? This is the
3.77.
3.7 is considered as the nominal voltage for the lithium ion cells. It is NMC chemistry. And okay. 3.6 is considered as the nominal voltage for the NCA cells, 3.6.
So generally, SOC should be considered 50% approximately for this, isn't it?
Yeah, actually, why is at a nominal voltage kept at a 3.7%? So means the nominal voltage that we consider, because it is the transportation. Once we do, so the transportation happens at a 40% of a SOC, and once you are storing the cells, so it should be kept at a 50% of it. So that's the same of a value comes. So that's why whenever a fresh shell you will purchase. Also, one thing that you need to remember always, that whenever you purchase a fresh shell, the voltage should be always at a 3.7 volt, like 3.7, 3.69, 3.71, that could be maximum. So maximum of a 0.1 variation we should be having in case of a NMC chemistry. And then in the NCA chemistry, that would be revolving around 3.6 volt. Also, few of manufacturers are making the cells at like, if it is the Panasonic cell you will purchase, so they will come at a 3.67 volt. LG cell you will purchase, they will come at a 3.67 volt. So the manufacturer specifies that what is their nominal voltage, and whenever you will be procuring a new shell, so just test the cells from the lot that whether the voltage is up to that level or not. If the voltage is higher or if the voltage is low, don't accept that cell at all.
Okay. Okay.
Okay, so this is the respective to the charge cycle. So we have raised the voltage up to 4.1. That's what is the without of a stress, and that's where it is considered as a 1. And we are going up to 3.07. So now what the thing is, once we are doing the prediction, so this is the real data. And once we will be doing the predictions in the modeling, it is the prediction that we will be doing. So how much the difference between our real data and the predictions we will be doing, that what needs to be calculated, right? Because only then you can find the error in the calculation. So this error, this difference method, once you have to find, so more number of data points you will have, the less error you will be able to see in your calculation, right? Because it is the root mean square error method that is called, where it is the what is the predicted value subtracted by the original value. This is the formula that is calculated in the, so this is a standard deviation. That's what is in the statistics. Actually, the term is the deviation, which tells you about the how much the deviation you have from the predictions to the actual of a values. So here is the F is the forecasted value. O is our observed value. So at a particular of a SOC level, what is your open circuit voltage and what is the actual open circuit voltage was. So that has to be subtracted. It is squared and then a square root is taken. And if it is the less number of data points you will have, so the higher error that you will be able to observe into this, and the more of because the less will be the averaging actually, and the more number of data points you will have, so averaging value increases and the error you will be able to observe lower.
So if I am correlating this correct, then in BMS, this function should be accurate enough. Otherwise,
Exactly.
what you have earlier told that might be it is giving the wrong indication and you are not utilizing the full capacity of the.
Yeah, that was if it is related to your yeah, if you are correlating the internal resistance with the OCV, so that's the a true reason for it.
Okay.
Because if it is just a 1 or 2 values we will be taking, so we will be always be in a problem, because just based on a 1 or 2 decisions, because if any dip that has happened, so that dip will be there for a small fraction of a times, and if based on that dip, if we are taking a decision, so it will always be a wrong decision. So that's why we need to have more of a values to average out, and based on which we take a decision. Similar of a thing, if you remember that I had discussed during that BMS, there was one discussion once happened that how do we take the data with the help of the BMS. So multiple of a time graphs are there, and the multiple in the multiple of a time sections, we are taking the value of the voltage or maybe the current that is getting drawn from the cell, and then average them out to find the total capacity loss. Remember?
Yeah.
So they are also
RMS is the only method to find out the error, or there are other methods
it is
to find out the.
actually there are the multiple of a ways are. It is the dependent on the models which we are selecting.
Okay.
Uploading this to you. So it is actually there are 4-5 methods. That's what is for this relation. All these are the models. So different of the estimations have the different of modeling methods. So right now we are actually in the electrical discussions once we are doing. So either it is the Thevenin model or the DP model. That's what we discuss. RINT model is the very similar one, a very small one where E minus IR. That
is a straight line.
Linear relation. You won't be able to get the polynomial relation out of it. It is the either the Thevenin model or the DP model, and the base for your DP model is the Thevenin. So that's why Thevenin is the a major one. And for Thevenin models to work on, these models like this least square method is called this method, which is discussed in this simulations and all. So it is the least square method. That is the most accurate method is. But this is not limited. There are the other methods are there, like characteristic parameter based methods are there, where you measure all of the values, IR, impedance, OCV, then you can measure the value of open circuit voltage. Thereafter, then how much the Coulombic loss that is happening from the cell. That's what also could be a method for the measurement of the SOC. We are taking it here as the open circuit voltage method, because this gives you a relation directly between the SOC and OCV. And then ML based methods. So what the genetic algorithm we are talking about, so it has a mix of actually the AI, the supervised learning actually, because we are first creating a data set. Right now, what I have shown you over here, this is the cell data. So this is a data set we have created. And this data set we are going to use for our further of a learning process, the algorithm. So that's why the genetic algorithm is a more used, because it has a mix of physical estimations and the modeling also, means the predictive analysis also. And that comes under the supervised learning. The total integrated word is called under the supervised learning. And that's why it is a more accurately gives the, so that's why this model is used. Okay, so I was talking about this RMSE. So this is just a one at a one data point. If you have to calculate the how much the differences are there in your root mean square value, so we can calculate. But if it is related to any of a parabolic relation or against of any of a polynomial relation, so we need to integrate these some of the values. Sorry, so from how many number of values we have, that's what, and then they have to be averaged out. Total value has to be averaged out. So that's why 1 to n, and they will be and then all the value collectively will be averaged, and a square root value gives you the final root mean square value. So this is used for the purpose that how much the deviation from your predictions to the actual value you have. And what I have asked you about the genetic algorithm. So this is the algorithm actually, which is used to take the base value. So there is a base value we have. This is the, sorry, like this could be our base value, the initial of a SOC, or maybe we can drop it up to 2.7 volts. And based on which we do incremental additions of the values to go up to the final value. Like another of example, if I take it is like we have an expression, maybe a square x plus b. There is expression that we have as a into x square plus b. Now here two of a different variables we have, A and B. These are the two different values we have. And we need to plot the value of A and B, but we don't have a function available over here. Is that right?
Yeah.
So, and so whenever we will be drawing any of a function, whenever we need to draw, so we need to draw it in such a way so that the value of A and B cancels out at the end. Because whatever the addition, if you have to solve any of an expression, and to solve that expression, if we add some values in that expression, so that expression at the end, whatever the value we have added, that should be cancelled, so that it does not have any of a cumulative effect on the expression. This is to in case of a mathematical expression solving, like you have the one left hand side, another right hand side expressions, and if we have to add the values on both of to reach to a conclusion, if we add some value on the left hand side of the expression, we add the similar magnitude of the a value on the right hand side also to balance it out. Remember the methods?
Yeah.
Expression solving. So similar of a thing we have to do in these genetic algorithms also. That
but in this case, what you were saying, that there are two variables, suppose they have to get cancelled, then either one of the variable we have to express in terms of the another, means A we have to express in terms of B.
Yeah.
Case.
So we need to create a function, and at the end, A and B together should be 0. The value, sorry, A and B, it means the in which terms we have represented them, that value is 0, right?
Okay.
So so this is, and this has to be optimized actually. So this once such kind of algorithms we are designing, so to reach to this value, so a minimal of an error, that one of the objective is that there should be a minimal of an error, and second of it, that it remain optimized. It means what? The like a parabola or any polynomial equation, once it is getting derived, the functioning of that algorithm should remain optimized, and it should not be any complex algorithm it should become, because we will have the multiple of equations for the derivation of it. That is called here as the population. We just feed it the value and it becomes as a population method. So the and that population goes in terms of 1,000, 3,000, 5,000, such kind of a population it becomes. So to keep the calculations in a least possible way for the optimization of the computing speed also, so it is the total algorithm that is called as the genetic algorithm optimization technique, and that's what we follow in these. This is actually used in the artificial intelligences or the machine learning, but here we have the data set actually available. So that's why the similar of algorithm is used in this. So what I will do that there are there is one note is this. This is the one note which has the discussions on this model. And apart from this, there are 2-3 more papers are there on the genetic algorithms. So I would like that first you go through those them, and maybe it will give you the idea on the genetic algorithm, because say only discussing the genetic algorithm will be, I think, more than 20-25 hours it takes, and that's out of scope of this. So it is the papers I will be submitting, uploading you. You read them on a weekend, and then we will have, because we have the again the modeling that is there in our next week session. So there we will be discussing about the polynomial functions, this genetic algorithm again. And if you have the queries, so that time we can discuss it more. So using this genetic algorithm, actually, what I was, so this is the data set we have. And based on this, we are going to get a relation between of our open circuit voltage and the SOC. So this is the formula. Actually, here the formula is this, which I had shown you earlier. This is the relation.
Root of it.
Yeah, this is the relation actually. And using this estimation method, we have reached to that it is a polynomial equation we have to derive. Now the question is that what should be the order of this polynomial equation should be. And the one thing is decided over here out of this discussion, that if it is the higher the numbers of our estimations and the higher the number of data sets and the data points we have, the more accurate of a method, or the more accurate of a output that we can get. So to solve this thing, it is the 8th order polynomial equation. That's what has been selected. And this has come, that the paper that has the discussion, how it has come. So actually for this also we do the calculations that what should be the order of the polynomial equation. And for this, actually, practically what it is done, that like based on the data set we have, we draw one like this is our real data. Maybe just I'm just depicting, it is not very accurate. And then these are the predictions that we do. Like this is the real lines. This is the SOC, and this is our OCV. These are the data which we have as an from the physical calculations. And then we have the predictions values. Now, maybe this one is the prediction. This one is the prediction. This one is the prediction. So at many of our places, we will have the accurate values over here. You can see accurate predictions we are doing. And at some of the places, it is the differences in them. Now, if it is the less order of a polynomial would be, so what we'll have? We will have the less data points. So our prediction, our actual real value and the prediction value will be different. The nature of the curve would change. Like if we have only 2-order reaction, 2-order polynomial or a 3-order polynomial. So here maybe 1 here. And another value maybe at this point. The third one is maybe coming over here. And in this case, our graph would be changed to like this. So there is a error in the calculation that is there. Now you may have a question that how I am talking about the prediction values. So we have to do actually using this genetic algorithm, we have to do a simulation or modeling, and in which we will be feeding the values of our initial open circuit voltage and the SOC value, and the function for the implementation of this genetic algorithm is given in our Scilab. So the paper which I will share you, that has the description. That
I have one question. As we have plot the actual graph, suppose whatever may be the readings which we have,
yes,
and we have plot that graph, then whatever may be the iteration method what we are following based on the order, that is the only thing which will differ the spread, or might be some another things are also factors for this. Because if the lower order iteration method if we follow, in that case the speed can be dispersed. That is understandable. But suppose higher like 8th order, what we have considered is considered,
Yes.
then in that case the speed is expected to be near to the actual. But is there any another method that another reason that the speed can be go away from the actual plots
Uh,
what we have?
yes, it might be like right now, I have not considered the aging impact. I have considered the environmental impact, that is the temperature, the ambient temperature. And I have not considered the bleeding impact. That is the if the battery pack design is not good, there is a cell to cell body sorting is happening, so that it leads to the bleeding current of battery pack. So these things I have not considered. If you will consider them, that will be have that will have an impact.
Okay.
Right now, it is the cell is in an unloaded stage, and it is the single cell estimation we are doing. Once we keep it in a battery pack, the values will be changed, and that's why I'm telling you that we have again a modeling. Once I will come through this battery pack calculations and all the design of the battery pack, then again we will be coming back to modeling.
Okay.
Okay, so that's why the so this is the reason that the higher number of order of your polynomial is selected. And to do this, actually, these are the practical estimations also needs to be done. It is not just a selection of any of a number that we have done. It is tested at a multiple of here. I think it is given in your also that these values, yes, yeah, the first order, third order, fifth order, and eighth order, 4 such iterations have been tested, and out of which these are the different of a k values that has been generated out of this genetic algorithm. And this was the nearest one value. The 8th order was the nearest one value. And that's why it has been selected for this. Okay, so this is the genetic algorithm is also used in your chromosome theory, where we have the this thing. Chromosomes gets in biology, there is a concept of chromosomes, right?
Yeah.
So here also the similar of a genetic theory is used. Actually, it came from there.
Okay. But these other iterative methods like the Newton-Raphson and Gauss-Seidel are also coming under this, or we cannot use that?
Gaussian theorems?
Yeah. Gauss-Seidel and Newton-Raphson is also there.
Yeah, there are the methods. The methods are also there for it.
Yeah, because those are also for averaging out. I'm not sure whether it is really useful for this.
Actually, the thing is that related to the Gaussian in the lithium world is little less used due to it is more of a model based rather than it does not have the estimations of including the physical quantities over there.
Okay.
One region behind of using this method where we have the physical data set and based on which we do the predictions.
Okay.
Okay, so out of this, the for here for your lithium, so this is the 8th order relation. This is, and in this we have selected the method is same as we have discussed yesterday. So the function and everything, and it has been it is against of a SOC. Yesterday we had a DOD as the consideration. Today it is the SOC consideration it is, and here the plot, that's what we are taking it as a like this. So this is from 2.8, that is the cutoff voltage level of your cell is considered, and then up to 4.2. approximately that has been considered for the cell level open circuit voltage.
Sir, one more question. Here, is it possible to feed the actual measurement data and to compare the way you have now shown on the paint? So now this is the
Yes.
iterative method output, and now if we plot some actual value reading.
Actual X and Y data that you want to feed.
Yeah. So in that case, we can see how much.
We can. Here we have given the range. So like here you see this is the range that we have given, and out of this range, see the values are here. This is your, I think. So see. This is the value actually that is coming, if you see.
Okay. So this is coming, but actual readings.
Same way we can give the range, no? Like readings we can give. There will be no relation at all in that case. You will have to give the here what we have given. You can try it maybe after this. So here we are giving the range, right?
Yeah.
For the SOC in place of it to feed the values. All of the values you need to feed in. And here for the plotting purpose, we are giving it like the SOC into 100 and we are calling the EBAT.
Yeah.
So again, for this, you will have to, for the voltage, for the open circuit voltage, you will again have to give a range.
Okay. So two plots can be possible on single paper.
Two.
So means one actual and one iterative method plots are possible on single graph, you mean to say?
Iterative not, it is the, you want to plot the real, like the data set we have available based on which you are going to plot this or something else.
Yeah, actually real value, suppose we have, the couple of minutes back you have shown the table where there are
that's what values. The similar of a thing I'm asking, that this is the real value we have.
Yeah, so if we feed that and whatever may be the iterative method what we are calculating, so at the same time whether we can plot both the graphs and see how much is the difference in the iteration or no?
Okay. We may try
for comparison purpose.
But we can do it in for the cell I have not done, but we can do it. Comparative, that the graph that you want to see, that one item.
Yeah, the same thing what you have now shown the.
Yes. We can do this thing.
Okay.
Only the ranges that we need to define. For one, you will use direct plotting function for the OCV and the SOC, and in one you have to apply the function for the iteration.
Yeah. And then we can overlap one over other, and then we can see how much is the
exactly how the differences are. We can see. You can also observe this thing like here it is a 0.001 is the difference for the reading. We have this difference of a 0.001 in this here. 002 0.001 is the differentiation. The real values, if you have the higher the difference, so how it is like we are taking a gap of a maybe 0.005 or maybe 0.10 if the gap that's what we are taking for the real plotting. How the graph would be different, that's what we can see. We can comparison, and that will give you the actual reason behind selection of the number of more data sets.
Yeah, correct. Yeah.
Okay, so for this, so I will be uploading this also on your script. You can take it as a reference, and once on the weekend you can read through this, and next week once we will have the battery simulation, so there we will be taking this thing again.
Okay.
Vyom, you were disconnected, I think, in between. Any question you have? I'm moving towards the next part of it.
Yes, sir. Sorry for I actually had a network problem. So my question here is that these SOC values that we are getting, these are also measured using some formula, right? Combination of the open circuit voltage and the current.
This data which you are seeing in front of you.
Yes.
This is the real data.
And these are measured by using some formula on the open circuit voltage and the current being drawn. Right?
Like the SOC. Yes. There is a SOC, like there is a SOC depiction formula means the peak is like a 4.1 is considered as a peak, 4.15 or 4.16 is considered as a peak, and that is taken as a 1, and against of which the representation is.
Okay. So
Okay, so
there is this theoretical graph which can be plotted for UOCV and SOC also, like based on that formula that we used to calculate the actual values.
yes, we can. That's what the similar of a thing I think Vikas was asking, no? That can we do the side-by-side comparative analysis? So we can do that. Like you want that we are applying a formula, and for the OCV calculation based on the SOC, and you want to plot a graph for it.
Because anyway, we are using these models to make a polynomial function and getting these values from the like measuring instrument, but the measuring instrument itself is using some function of UOCV to calculate the value of SOC. So why not like directly use the same function to plot the graph?
No. See, SOC in the instrument which we are seeing that is not taken into consideration. It is the percentage representation. That's what we take. And if you see here, that is not represented as a percentage. It is the 1 is the considered as the peak value for our SOC.
Yes, so I understood that percentages have been converted into decimals. But SOC, the value of SOC, either it's 95%, so it has been represented at 0.095. But this SOC value was calculated in the measuring instrument by using some value of UOCV only, because SOC is not directly measured by the instrument, right? Only voltage and current we are measuring.
Voltage and current only you can measure. Yeah, we can. Yeah, so you are asking me that why not take that formula in and
yes, instead of using these models, why not use the direct formula which the measuring instrument is using for SOC and UOCV graph? And
that's what the similar of a thing. That's what the discussion was, na? That using this is the plot. That's what we do. Like this is the plot which we have done. So it is based on our formula, right?
Okay.
And how much this is related, how much this is accurate to our physical values, that's what the calculations and the predictions and the real values differ.
Okay. So based on that, you are also calculating the standard deviation of the differences. Okay.
So that standard deviation is through your RMSE, and this genetic algorithms give you the value of different. These are the fit of curves. So multiple of a point. That's where you will be multiplying the SOC value at a multiple of points, and those points are represented as here K0, K1, K2. That is called the coefficient of your curve. So that's what the coefficient of the curve we are getting through the genetic algorithm.
Got it, sir. Okay. And for predictions, we can use the combination of some formula and the standard deviation, like for predicting the like.
The formula. Yeah, for using the formula we are predicting, and how much the difference in our prediction, that prediction and the real value is. That's what is the standard deviation we have.
Okay.
Okay. The thing is that was SOC is for our reference only. SOC does not have any of a relevance in the real physical quantity of the cell. The real physical quantity of your cell is voltage, current, and based on and using these two, we can have the capacity and energy. As the capacity is fading, so that is leading, or that is dropping your fading means depleting. It does not mean that life is fading. It means that if the capacity is getting used, if the cell is getting used, the capacity is getting utilized for the any of application to run. So that the SOC that is leading to the depletion of the SOC value. And once the capacity is fading, specifically in the NMC cell, our open circuit voltage is also dropping down. And that's what the relation we are deriving out here. So that's what the thing is. Any more questions?
No, sir, we can move ahead.
Okay, so I'm moving towards the calculation battery pack calculation side, and in the meantime you can do a study on this. Okay, so the battery pack calculation, once we are going towards the battery pack design actually. So there are the electrical design, then you have the mechanical design, then you have the thermal design, and at the end, it is the safety that comes, that what are the safety measures should be there in your pack. And at the end of all of this, it is the homologation process that is required for your battery pack. So that the any of a certifications that you require, whether for the EV application or ESS application, so that could be get through the authorities. So the base of your electrical design starts with the cell battery pack calculations, that is also get the capacity estimations for the battery pack for any of an application. And as per the capacity estimations, you will require the number of cells to be connected in a series and parallel from the electrical rules, so that the particular of a voltage or the particular of a capacity from the pack that you can get, because your cell, only one cell has the very limited capabilities in terms of the voltage and the capacity both. So the first of the thing that it starts with the cells in a series, and the series combination gives you the accumulation of the voltage. So once the cells are connected in a series, so their opposite of the terminals are connected together. They are like one of the positive that would be connected with the negative terminal of the another of a cell, and the total of the potential that would get added over. So once you will connect all the cells in a series, so in the beginning, there will be a maybe positive terminal, and at the end, it will be the opposite terminal, like a negative terminal we have. And total of a potential, once you will calculate, so it is the added potentials of all of the cells that we have. So we can take it a reference of maybe a water pump. So that water is getting inlet inside of a pump. The amount of water remains the same, but as it is the from one pump to another, it is passing through. So their potential gets increased on, and the force that will also, in case of the water, jet will be there. So similar of a case, in case of a cell also, the potential is get added over in a series connection, but the amount of a current or the capacity that won't change, it would remain the same. So once the cell is connected in a series, the negative of one cell is connected with the positive of another, and that's how the series combinations are continuing. Once we have once we connect all the cells in a series, there is an external resistance that is connected as a load, and that load is connected between the first and the last cell. So like in this case, and these connected terminals will be of an opposite polarity, only then the current will flow through. If like a switch, if there is a closing switch, if it closes, so the current will start flowing through. So if we have n cells who are connected in a series, and each is having the EMF of E, the internal resistance of each of the cell are R. So combination that could be, so if you have to replace this, all of the combinations of a cell through a single cell, so their EMF will be how much? It is NE.
N into E. Yes.
And our internal resistance will be NR, right?
Yeah.
So how much the current that would be flowing through? It is
So This is NE divided by NR.
And
And the resistance, what is the external resistance?
external resistance also we need to add in, right?
Yeah.
Yeah. Now, if it is our internal resistance, the cumulative internal resistance is very smaller than our external resistance. That is the ideal case that we are expecting. So it would be the NE by R, because NR is a very, very, very small value that can be omitted out.
Yeah.
And if our internal resistance, total of our internal resistance becomes quite higher than our external resistance that is getting connected, so our voltage would be dropped to how much? E by R.
Yeah.
And so maximum, so that would be a short circuiting case for our circuitry, right?
Yeah.
And so because of the our internal resistance becomes quite higher, that is obstructing the flow of the current through it. So maximum current can be drawn from the series combination if your external resistance is very large compared to the equivalent internal resistance. So this is the ideal case. That's what is there in a series circuitry is.
Yeah.
And if it is the by some mistake, if we have connected, there are the n number of cells are there in a series, and p cells are maybe in a reversed, they are added in a reverse polarity. So they will drop the total of equivalent EMF. And this will be this would be the leading to total number of cells, p number of cells are connected in a reverse, so they would be omitted out from your total series combination. So that's why n minus p, it is into E minus PE, the p number of cells are in a reverse, so that they have to be subtracted. So n minus p, and your n minus 2p into E, that would be the equivalent EMF. But there is no impact on the internal resistance would be, because it is a directionless. So I would be n E upon n minus 2p into E upon nr plus r, it would be. And for our simplicity, we are taking it as the multiplication of n, or if it is the n number of cells, it is so n into E we are taking. But actually, for a general case, in case of a battery pack, it won't,
So
because
I have one question here. This
yeah.
E equivalent, where n minus p into E minus p minus E.
Mm-hmm.
So whether this p is a part of n or how it is?
It is not the p.
Because if n I consider as a total number of cells, then
Yes.
Out of that p are reversed, or the n is separate and p is reversed. Because n is separate and p is separate, then in that case this equation might not satisfy. That's why
it is the total. Yeah, that's why the if in series combination of a n cells, so total of n cells we have, which p cells are reversed. That's why this formula we are using.
okay.
If it is the n and p, these are the separate, so maybe they will come in a parallel.
Yeah. Okay. No, because here again R is equal to NR, they have considered. So
R is equal to NR we are considered because it is the total number of cells
that are in series,
right? So so that's why this thing will be that the total of n cells are there, out of which p is in a reverse direction. Maybe few chunks, it is the 10 cells we have, out of which maybe 2 or 3 is in a reverse direction.
Mm-hmm.
So cumulatively they will drop the potential, but your internal resistance is a directionless thing. So that's why it is get added in a series. Is that clear?
Yeah. Okay.
Okay. So our in case of a battery pack, I was talking that there won't be any difference of a potential, because In the battery pack, we have the same potential of a cells that we take during the selection process and out of which the battery pack is made. But actually your equivalent EMF is the additions of all of the EMF values. So E1, E2, E3 could be different, and they will be added together to form the equivalent EMF. And similar is the case for the internal resistance or the resistance also. So the formula is coming from the addition of all of the values. Then we have the cells in a parallel connection. So the voltage, if you are forming a battery pack out of the combination of the cells, so the cells are connected in a series, and out of which we can make a required amount of a voltage for the battery pack. But if it is the capacity, that's what we want. So the series in the series combination, the capacity would remain the same. It won't get added over. So for that thing, there is a parallel connection is there. Parallel connections of the cells. That's what we do, in which the terminals of the same polarity would be connected together, and the two of the terminals that would form out of the two different polarities will have the potential across the cells as a same, whereas the capacity that would get added over throughout. So if our cells, those are getting those are connected in a parallel, so it is the representation like this, where we have the cells, positive terminals connected together, negative terminals connected together, and across of both of the terminals, it is the one external resistance that is connected. So M identical cells of EMF E and internal resistance R is connected in a parallel. So this combination, if we have to replace this thing, so in this, the potential will remain the same. It will remain the E. And our internal resistance will be how much? It will be R by M. If there are the M number of our cells are, so it would be R by M. And the current that would be I is equal to E by R plus R by M, right? If your R by M is so in the case of the parallel connections, the internal resistance become quite lower compared to a single cell internal resistance value that would be divided by the number of cells connected in a parallel. If it is very less, then I is equal to E by R. And if your R by M becomes quite higher, then I will become how much? M into E by R. Because this gets omitted and this M comes on top, and it is the M into E by R. So this will be the short circuiting case in case of parallel connection circuitry. So maximum current that could be drawn from your parallel combination if the external resistance is smaller as compared to the net internal resistance of the cell.
Okay.
Any questions that you're asking?
No.
Okay. Okay. Now, respective to the cell, this was the impact on the voltage and the capacity, but what would be the impact on the energy and others? So in case of a series combination, it is the V pack of your will be multiplied by the number of cells those are connected in a series. The pack capacity would remain the same as your cell capacity. The internal resistance would be added over. So that's why how many number of cells are, it would be multiplied. The energy is how much? It is E is equal to V into C. So it is the V will become how much? 4 into V cell. That is the total battery pack voltage into the capacity C cell. But in of a parallel combinations, it would be the pack voltage would remain the same as of a cell voltage, whereas the pack capacity would be multiplied by the number of cells. The internal resistance would be divided by the internal resistance will be the internal resistance of a single cell divided by the number of cells connected in a parallel, whereas the energy would again from the V into C, and here the multiplication of the number of cells will be in the capacity of the cell, that will be multiplied by the potential of a single cell. So that is the direct series or parallel connections we are doing. So for this, but actually once you are going in a battery pack design, it is not only the series connection or not only the parallel connection that you will be doing. In case of a prismatic cells nowadays, it is possible that you will be doing only the series connections may be possible, because maybe for an example, you are making a 2-wheeler battery pack using a prismatic cell, or maybe you are making a 3-wheeler battery pack using a prismatic cell, and that cell is of a 90 Ah of a capacity. So you have to do only the series connections, and you will have the required amount of a battery pack in your hand. But if it is the cylindrical cells you are using for the battery pack forming, so cylindrical cells have the limited amount of a capacity like 3 Ah, 4 Ah, 6 Ah, such kind of a capacities you will have. The voltage will be in the range of a 3.7 or 3.2 for the LFP. So you will have to do a mixed arrangement of the series and parallel. Now there are the two ways of arranging the series and parallel combinations. One in which is there in front of your screen. In this is called the in this it is the parallel connections of the cell we are doing first, and thereafter these parallel connections are called the modules. So these are called the cell modules. Separate. In this parallel connections of a cells, the potential across the cells will remain the same, whereas the capacity that would be added over as per the number of cells connected in a parallel, and then they will be added in a series so that a final battery pack voltage we can have. Like this is a 10 Ah, 10 Ah, 10 Ah, so 30 Ah module is this, then 30 Ah module is this, and each of the module is having a voltage of a 3.7 volt. And once we will be connecting them, so maybe 4 such modules, so 3.7 into 4, that would be the 8 and 14.8 volt, and 30 Ah would be the capacity and the voltage would be. So that's what is. So this is a one way of doing the things, connecting the cells in a parallel to form a module and then add them in a series. There is another method is where we connect the cells in the series first. So this is a series oriented connections we are doing. Here it is the series arrangement we are doing, and then these cells are connected in a parallel. So out of this it is the 14.8 volt, 10 Ah. This is also 14.8 volt, 10 Ah. And once they are connected in a parallel, so they will be forming as a battery pack of a 14.8 and 30 Ah. So in both of the case, we are getting the same output for the battery pack, but any idea that which one method should be good or which one should we use? What is the difference? Are you able to observe any kind of a difference in these two methods?
Yeah, I think in this method, most probably the earlier one, all cells will be discharged almost at the same level, but in second method that might not be the case. Or in the first method, if we see, then the resistance offered by the battery pack at the total level may be lesser, but in the second might be that is higher, I guess. I'm just guessing because I have not calculated.
You can calculate. You can calculate. Just I want answer from the Vyom also. Vyom, you have anything to tell about the both of the combination?
Sir, I think the resistance would remain the same, but this point regarding like the current being drawn from the different modules. So that also, I don't think there would be a difference. It would finally come down to how do we want to physically connect these modules together and like balancing it. So which method seems more suitable for that?
You have raised a point related to the balancing. So that is a valid one. Can you explain a little bit about the balancing, what you are talking about?
So, sir, one would be electrical balancing that as in like all the cells connected in series, if they are like not equal current is being drawn from those cells, so one of the cell might become like less than the required capacity before other cells, and it might cut off that like series altogether according to the BMS. But if the cells are like getting if constant current is being drawn from all the cells, that is the ideal scenario. So that's how, that is one part. Apart from that, like these cells, these modules have to be eventually joined together. So if we are connecting these cells in series, and then one module of all the cells connected in series, and then we are connecting it in parallel to other cells, that would be easier to join in my opinion, because all the positive terminals from all the modules you can connect together, all the negative terminals from the module you can connect together. But in that case, you would have to figure out an arrangement so that negative positive of modules are together. That's how, because welding it might become a problem to join those cells. That these are the things.
Welding is easier in this one if you will do it physically.
Sir, one more
Yeah.
thing, that number of joints in this earlier is less as compared to the second one. Isn't it? Or no?
Number of joints related to the BMS, or it is the weldings?
At the battery pack level, the number of joints appear to be more. Might be that will offer some
I
again.
think the welding
additional
part
range.
Vikasji is talking about.
Yeah.
Okay. There is a one thing that I will put first, and thereafter maybe you can think again.
But
So
resistance, definitely what VM is saying is correct. I guess resistance will not
okay,
change.
just let me calculate. It is in front of you. So it is R by 3.
Yeah, I need 4 times.
And that would be multiplied by 4. So 4R by 3, right? That is right.
Yeah.
And in this, it is 4R, and
Same.
right?
Yeah.
And 4R by 3, it would be the total one.
Yeah, same resistance.
Same resistance it is. Okay. See, the thing is that respective to the BMS, balancing actually we have raised, and that was the valid thing over here. Construction and everything is the similar, but that does not make much of a differences, because you have to join all of the terminals. The thing is related to the BMS. So in this approach, we get a in this series oriented approach, we get the flexibility, or we get the opportunity to monitor each and every cell, because in the BMS we have the as an input in the BMS at a cell level, we only can measure the voltage of the cells, the terminal voltage, or the open circuit voltage, actually what open circuit voltage we will consider. So using the BMS, we can only measure the voltage across the terminals of the cell. So if it is a series oriented connection, and based on which we do all the kind of decisions, like how much the balancing would be done, or your how much the capacity that is left, that is effective to the NMC cell I'm talking about. If it is the LFP, then the total current also gets considered. But for the NMC specifically, because this is what we have considered over here, because in the mixed arrangement, it is the NMC that is used most. So in that, using the voltage as the one of the parameter for knowing the status of your cell. So if we have the measurement of each and every cell, so more accurate of a balancing our BMS would be able to do. Am I right?
Yes, sir. But in the previous case, why can't we have like connection to each of the cells?
I'm just coming. So in this
BMS.
arrangement, we have the connection with each
Yeah,
cell for the voltage, and we can monitor the status of each of cell in this, right?
yeah,
Right.
that's true.
But in this, is it possible to monitor each of the cell individually using the BMS?
No, because this will mislead it, because there are the 3 cells which are in parallel.
There are the 3 cells connected in a parallel. So even if like this cell is got open circuit, or if this cell capacity is getting faded faster compared to the 2, but potential, there is no impact on the potential will happen.
Yeah.
So even if this cell is gone bad, but potential would remain the same, we will not be able to figure out that which one cell is going bad. Or maybe total of the capacity of the pack would be dropped because this cell, one cell is not taking the full amount of a current, but still we won't have any of a knowledge that which one cell is gone bad. Even it's also possible that this cell get open circuited. This cell gets open circuited, and but there is no impact on the potential would happen because other 2 are having the same potentials. So that
But
is
even if connections are made individually to each cells, this would be the case that potential.
like this becomes open circuited in this case.
No, in the previous slide only, if we are doing physically, the wires of the BMS are connected individually to the terminals of these cells in parallel. Still, it would show the voltage 3.2 even if one cell is short circuited.
Exactly. So
Sir,
Because the
I have
physical-
one question. If these are considered as individual modules, suppose, and earlier what we have studied that any cell which is having, say, lower SOC, that will define the SOC of the total module. So in that case, how will be the behavior of the series and this parallel?
that lower SOC, not actually the lower the capacity. Means yeah, that SOC is related to the capacity. That's why you are telling the term as the SOC, but actually it is the capacity that is fed out of the cell.
Okay.
So yeah, so in this case, like if this is the cell whose capacity is fading faster, so it is going out of the balancing. So this would become the weakest cell in this module, right?
Yeah.
So if the discharging or the charging that would happen, so the same at the time of the charging, what would happen that this would get charged, this cell will get charged maybe up to, if in terms of the SOC I'm talking, maybe this is get charged up to 90% of a SOC. This also got charged up to maybe 92% of a SOC during the charging, but this is charged only up to how much?
40%.
So what will happen in this case? Once the balancing algorithm would run, so it will once the charge, like if it is the passive balancing we are doing, so in that case it will observe the total of a capacity of the battery pack by adding the current or the capacity of all of the cells, and in this, at this module level, the capacity would be lower compared to the other one.
Yeah.
Because the capacity or the current, if it is getting discharged, so at this module level we have the lower values. If all of them are getting charged up to 90% of a SOC or the capacity related to that, but this will have because these cells are connected in a parallel. So total of effect will be lower in this case. So
in that case means other two cells will get more loaded or stressed.
Yeah, this will be during the charging process. These two cells will be charged up to this level, and stress condition it will happen compared to this cell. But once it is the balancing will start happening, so it will see that this is the module. It is having a lesser of a charge. So other modules will be discharged up to this level. Maybe together of it is the maybe together of an impact of the SOC comes of a like a 90 maybe 89% of this module, and other modules are charged up to 90. So what will happen during the balancing process, all the other modules will be discharged by 1% self discharge across discharge circuitry is there inside the BMS, and across that discharge resistor, there will be 1% of a discharge of the current that will happen to bring the SOC at the 89% level. So at the time of a charging, you have fed the value up to the level of a 90%, but during the balancing process, that 1% is discharged that has not been utilized, and the range of your pack will also be lesser. That is being driven by the a lower module value, and the excess amount of a charge or excess time you have taken for the charging of the battery pack that has gone wasted.
But that might be the case in series also. No? Suppose there is also one cell which is having capacity of 50%, then the total voltage level will drop down for the battery pack.
Yeah, in both of the case, the issue is there, but here in this case, it is easier to find that which one cell is. So that's what the monitoring purpose. Actually, practically, this method is used. If you will take a battery pack, any of a battery pack you will open out, you will see that this is the method that is used.
Okay.
Because it is the BMS, it is the region of the BMS. It's here in this, it is the like a 10S battery pack we are going to make, for an example. So in the 10S battery pack, total of 10 such points you will have for the measurement.
Yeah.
So, and if it is if you are having such kind of an arrangement, but if it is the same 10S, maybe 10S 3P battery pack there is a two things will always be there. So if it is a 10S 3P battery pack we are making, so total of 10 such points you will have for the measurement. But if it is the parallel module connection, and if it is the series oriented connection we are doing, so we will have how many number of total points? For each of a cell, we have the point, and the 13 number of points we have, right?
Yeah.
So the BMS which is available is BMS is available like in a 10S or 10S, 12S, 14S, 18S, such kind. BMS is not available like in a 30S series or maybe 100S series. If such BMS you have to use, so then it is the master slave BMS that is used, where we have the multiple of a slave BMSs that gets connected on a master, and then they are used for any of our application, and the application becomes quite expensive in that case. So that's why as a normal battery pack, if you are taking, so it will be the parallel oriented connection you will be seeing, and the BMS is of like a 10F, 10S, 12S, 14S, such kind of a BMSs are there. And in this is the problem that will remain always, that which one cell, if in the parallel of a combinations, which one cell is gone below, you will not be able to observe.
But this master slave, what we were talking about, in that case also the slave is going to monitor the module level voltage. It's not might be at the cell level.
No. if it is in this, if we have to do so multiple of the slave BMSs, it is the arrangement is like these slaves are of like a tennis pack. NS. So maybe it is the 10 cells are connected in a series. So for each of the cell, these BMS can connect. Then for this also, and all of these BMSs, all these slave BMSs will be communicating to a master BMS.
Yeah.
So more number of sensing points we get using the master slave communications.
Okay.
Also,
in this master slave also, in the slave level, it is monitoring the cells,
yeah,
individual cells.
It is like if it is the mixed arrangement, series oriented mixed arrangement we are doing, then the slaves will be monitoring the cell level.
Okay.
Also, it is not like that in this parallel arrangement master slave is not used. It can be used like if it is a maybe this thing 400 volt battery pack, traction battery pack you are making, right? Now for this the a series would be how much? It is in the range of maybe I think more than 100. 400 divided by 3.7 you do. How much it comes? I think 108 or something it would be. It is 108, right? For 108 numbers of cells will be in a series. Now there is no such BMS available in a single assembly which can have the feasibility of measuring 108 series, 108 cells in one BMS. So there also the master slave architecture would be followed at a module level. But it is so the master slave is not the restriction factor for this. It is the number of cells, how they are connected, and how many number of cells we have to monitor in the battery pack. That's what would be the method for the selection of your BMS would be.
So these BMS which are available in the market, 10S, 12S, these only have 10 like measuring connections which can be.
Yes,
and
10
so
measuring.
we necessarily if we are making a 10S 3P pack and using a 10S BMS, we necessarily have to make modules of 3 cells in parallel and then connect them in series. That's how we have to.
Yeah, actually the BMS once you will be purchasing, they don't have a rating of a 3P or 4P, something like this. They sold like a 10S BMS, 12S BMS, 14S BMS. So it means that these number of cells are connected in a series. Now, how do we take a reference of the P connections? So they have the current rating.
Yes.
Peak current, average current, and the minimum current, based on which we select them for the period.
So if we have, let's say, this kind of connection we want to make, which we have used in the previous slide, can we buy a 30S BMS? Yes. Can we buy a 30S BMS and do like make a 10S 3P kind of pack only like this it has made and do connections to each of the point? Will the BMS and program the BMS likewise? Would it work?
But 30S BMS is available?
Theoretically, I am asking if like, let's say if you want to do it for 10S or 12S, 4S के लिए ऐसे करके, is it theoretically possible?
It is possible. Like if you are making a you are asking me that if it is the such kind of arrangement you are making out of maybe 10 cells, and then you are taking a 10S BMS and connecting them, so it is possible. Okay. But the capacity would be very.
Program the BMS in a way so it knows that the connection has been made in this fashion.
If it is a programmable one, so BMS are also of 2 categories. If you are the ready-made BMS you are taking, so they could not be programmed. They just the connections you can do only into it, and they will do the balancing. It does not there is a no meaning for them that how the connections are made.
So individual cell balancing actually does not depends on the connections of these cells, right?
Exactly. BMS actually BMS will be doing the balance the individual level, because
Right.
BMS has only the feasibility of measuring the voltage through the connection. So it is working on the individual cell, but because you have connected the cells in a parallel, so that's why all this module is considered as a single cell over here. So this is a one single cell total for the BMS.
Okay.
So whether you have connected it in a parallel arrangement or in a series arrangement, it is irrespective for the BMS for the connection perspective. But because once we are doing the mixed arrangement in the series oriented, specifically for the applications we are talking about like a EV or solar and all, so it is the more number of cells it becomes. So that's why the general BMS is not able to handle them, and that there the master slave BMS is required.
So if we are using a ready-made BMS 10S category, then we would have to make like 10 modules of 3 cells in parallel each. That's how, like that is a
Yes.
restriction which
That
comes
is
on
the
battery design.
exactly. That's the restriction from the BMS point of view.
Okay.
The shortcoming of this is that you can't monitor the individual of the cells, and once it is the and if you are not able to monitor, so maybe any of a machine that you want to develop, or maybe any of a method that you want to develop to find out that which one cell in the pack is going low or which one capacity is fading, you will not be able to observe them. You have to break your battery pack, and only then you can test each and every cell and find that which one cell has gone bad out of those 100 cells for your battery pack. And so any of a online monitoring method, like any IoT based monitoring method of your battery pack, if you want to develop that would be working on the individual cell level. So there this series oriented mixed arrangement would be working. You can't be working on the parallel arrangement. If it is on the parallel arrangement, any of a IoT based methods you are applying, so always the error that it will remain in the design, that it will be giving you the nature of all the modules together. It will not be able to tell you the individual of a cell. So that's what is also one of the reason that the standard BMS you purchase, that is available from the China and all. So they don't have the communication features because they are not able to tell about the battery pack more. And once it is the master slave BMS comes into picture, so they are able to tell you, because with the help of them, we are able to monitor the each and every cell. So they are able to tell you the status of each of the cell, and they have the communications and the IoT, everything integrated with it. So that's why the design difference is there. Any more questions on this for the discussions?
No.
So if it is a 4S 4P pack we are having, so it is the V pack. It will be the number of cells who are connected in a series. C pack would be the number of cells connected in a parallel. If it is the equal number of cells are there in a series and parallel, so it would be the division and multiplication both. So that's why the voltage of the internal resistance of a single cell becomes the internal resistance of your battery pack, and E is equal to V into C, the formula from there. So if it is the n number of cells, and n into m would be the total. So if you have to replace this, so here the series and parallel combinations both we are having n number of cells in a series and p number of cells are in a parallel. So total number of n into m into p, that is the total number of cells. The current in the circuitry will be maximum when it is the R by N plus R by M is minimum. From this derivation, E by R plus. I is equal to E by R by N plus R by M. So if this factor becomes minimum, so the I value will become higher. So that's where the circuitry current is higher. There is a small question is that we have a identical cell, each of a EMF 2V, and there is an unknown internal resistance which is connected in a parallel. The combination is connected to an external resistance of a 5 ohm. The terminal voltage becomes 1.5 volt after connection of this external resistance. What is the internal resistance of the cell is? So it is a parallel connection. So I is equal to E by R plus R by M. So R by R plus 3. Potential difference would be I is equal to I into R. So here I is what? E by R plus R by 3 and into R. So E into R. And I is being replaced by this E by R plus 3 and R is in a multiplication. So R by 3 is equal to ER minus VR upon V after solving of this. And R will be 3 into ER minus VR upon V. After solving of this, it would be this R is our internal resistance value. And if we put the ER is our 2 volt, the VR is our 1.5 volt, and then the potential, sorry, V is the 1.5 volt, the and RV is 5 into 1.5. Same way, ER is 2 into 5. The E is 2 volt and R is the 5 ohms. So after over solving, it is the 5 ohm is the internal resistance. That's what we get from the cell. Now for a battery pack. Okay, the first question for us is, we need a battery pack of a 0.5 kWh. Which type of a cells should I use and what would be the pack configuration? Any answers? Is the question correct?
Yes.
Yes. So I guess, sir, for the pack configuration, we need one more information, either the voltage.
So I have not provided you the enough information here, so you can't be able to tell me the configuration or the cell about any of a thing. So it is the voltage that is necessary once we are talking about the battery pack. So it is the voltage that is the necessary factor, and then the current or the capacity. That's what. Current is also not, it is the capacity or the energy. That's what is required. The current could be varying. Depending on your C rate, the current would be varying. Current would be of the application, but for the battery pack, it would be the capacity or the energy. That's what will be the factor, I should tell always. So this is not the right question actually. Then we have a battery in a configuration. What is the norm in this? It is written as a ICR 18650. That is the model number of the cell is 18650. It is 6600 mAh and 3.7 volt. That is the rating of this pack is. So what is the nominal voltage and the nominal charge capacity of each cell is? And what is the energy? Nominal voltage of this cell is how much? This is a
3.7.
It is the 3 cells it is seeming inside of it. In this pack, it is the 3 cells are there. So 3.7 would be the nominal voltage. And what would be the charge capacity of the cell, individual cell?
6600. Same.
How much it is?
2200 mAh.
2200
mAh.
Yeah, 2200 mAh. It was connected in the parallel.
Yeah.
And if it is the energy they are asking me, so E is equal to V into C. So that is 3.7 into
66.
in
Cell or battery pack?
and
Battery
that's of the
pack.
battery pack they are asking. So it is a
Then 6600.
6.6 actually, no? Because E is
Yeah,
the capacity should be in terms of a AH.
yeah. That's
So that's why the 6.6. Okay, that's it. Okay. Now one more question is, I have a battery pack of a 375 volts to be made of a 200 Ah of a capacity. So our V is 375 volt and our capacity is 200 Ah. For a luxury car, we have to make this thing. This capacity is measured at a C/10 rate. One battery pack will be made up of a 3.65 volt 4 Ah cylindrical cells, and another pack will be made up of a 3.65 volt 50 Ah prismatic cells. So there are the two types of cells we have. One is a cylindrical one, another is a prismatic one of the different of our ratings. Now it has been asked that what is the NPMS configuration for each case. So if you are using the cylindrical cell, what would be the configuration of your pack? If you are using the prismatic cell, so what would be the configuration? In both of a case, what would be the total number of cells in each of them? And if in a module of n parallel cells, in a module of n parallel cells fall open during the operation, what would be the impact on the pack voltage or the pack capacity? Can we calculate this? Our V is 375 volt.
375 by 3.65, around 103, 104 cells in series and 50 cells of 4AH in parallel.
Okay, so you are dividing 375 divided by 3.65, right?
Yes.
So it is 102.73, it comes. Now my question is whether it will be 102 or 103.
103, I guess we should go.
Series will be the 10 and this thing. Parallel will be how much? It would be 200 and divided by 4, so 50. In case of a cylindrical. Now there is I had a question that whether it would be 2 or 3. So if it is a 2, so in that case our voltage would become how much? 372, right?
Right.
And if it is the 103 we are taking, so it would be 3.75.95. Which one should I take over here? What would be your decision?
Sir, so anyway, 3.65 is the nominal voltage. The actual voltage of the cell, depending on SOC, would range from 4 point something to 3 point less than 3 point something. So I guess to be on the safe side, we should take the closer value to the nominal capacity of the pack that we require. 3.7, like I would take 103 cells.
But it will cost you 50 cells more for your pack.
That is true. That is true.
Exactly. So in case of a larger battery packs, this is a business thing. It is not a technical thing that I'm talking about. But for what happens practically in the case of a larger battery packs, this is for a car. That's what we are making, right? And for the cars, the powertrain starts from the 350 volt that goes up to 400 volt limit. So even if we take it as a 102 number of cells in the series, there is a no impact on the powertrain or on the capacity will happen much, because respective to the total range of this voltage, the difference of a 3 volt that is in the nominal voltage range will have a very small impact in the voltage range, right? But that can save you 50 number of cells in that case. So a little of a battery pack cost could be lower. So depending on that, how much margins or how much you are playing with the things, technically it should be 103 number of cells. But if you are really tight on the margins, you can play on the 102 also. It won't have the higher of an impact. Okay, this thing is clear, the number of series selections.
Yes.
Yes.
It is and if it is the prismatic cells we are using, so same 102 or 103 will be the 103 will be the series combinations, and then it is the 4 number of cells in the prismatic parallel. So this configuration is clear. Total number of cells also we can calculate. It is the n into p. In one case it would be 103 into 50. Another case it would be 103 into 4. Now the question is that if in a module of n parallel cells in a fall open a cell in a module of n parallel cells. So it is asking that you are making a parallel combinations and then the series. You are making. So this is a module, and then they are connected in a series, another module. Now, if one of the cell that falls open, find the resultant nominal pack voltage and the pack capacity. For
Pack voltage will be same.
Pack voltage will be same, right? There is no impact. But what would be the impact on the pack capacity?
So that will be reduced by the particular cell capacity, I guess.
In case of this cylindrical, there will be more impact, or in case of a prismatic, there will be more impact.
Prismatic will be more because one is having a more capacity, so it will.
Yeah, because the 50 Ah is the capacity of a single cell. So that out of the 4, the 50 goes out. So actually it will be the 150 Ah of the pack capacity that would remain if it's falls open. And in this case, it is only the 4 Ah capacity loss we are having. So there is a less impact we will have. But there would be the impact, the capacity of the total battery pack would be lost. But if this is the same case happens in the case of a series connection, what will happen? Like now we are making a series of 103 cells. One cell gets open. What would happen?
It is I think the whole series will open.
What will happen?
Whatever that depends on the position of the cell from where it is. No, even the no. Those connection will get open. No, total
connection exactly gets open. So total of a pack voltage would be you will not be able to measure, right, due to the connection. So there the individual monitoring is required. Jom, is it clear? Any question?
No, sir. So one full parallel series would be cut off from the battery pack in that case. So the
one cell out of the parallel is get open, so that would get cut off. Yes. So that reduce the capacity of the total battery pack. Any questions?
No, sir.
Okay, then we are moving towards little another one. So here we had given actually this till this it is the problems where we have the voltage, capacity, everything is there based on which we are finding the configurations. But once from any of a EV manufacturer will contact you for a battery pack, so he will not give you real in real world problems. He will not give you the voltage. He will not give you the capacity and all. It is the capacity. That's what you need to find. Actually, from the powertrain side, the data comes, and this data comes in this form. Like we have to make a battery pack for an application which should give a range of like a 300 kilometers. And for going on this 300 kilometers, the average power consumption is 100 watt-hour per kilometer for the motor, and 8 watt-hour per kilometer is there for the extra load that is connected. Extra load that is connected like your maybe air conditioning system, lights, any of the thing that is get connected, that is taking 8 watt-hour per kilometer. And the overall efficiency of your battery pack is 0.9. The powertrain is of a 400 volt systems. The cells he is going to use is of a 3.7 volt with a capacity of 3000 mAh. The peak discharge from the cell, that's what we can do it for 3C rate for 10 seconds. The continuous discharge we can do of a 1C rate. Now we need to suggest him the capacity of the pack, what he should use, what should be the configuration of his pack, and then how much the power his battery pack can deliver. How would we calculate? Here we have only one parameter, that the voltage we have.
So for 300 kilometer range, we need 108 watt-hour per kilometer. That would
Exactly.
mean 32.4 kilowatt-hour pack we need to power this vehicle. So at 400 volt, we would divide 32400 by 400 to get the AH capacity of the AH capacity required to make a.
But we have an efficiency of a 0.9 also.
Yes, so 0.9. Okay, so again we have to divide by 0.9 to
exactly
slightly more capacity than around 35 watt-hour.
36,000 watt-hour per kilometer is the 36,000 watt-hour of the energy. That's what we require in this battery pack to cover all the 300 kilometers. Yeah, Vikas, you were asking something.
No. Actually, I was telling the 300 kilometers if we have to travel and the consumption is 100 kilometers, 100 watt-hour per kilometer, then straight away 30,000 watt-hour what we need. So from that also, is it possible to calculate or not?
Yes. This is the same thing. That's what we are going to.
Okay.
So 36,000 watt-hour is the total of energy of your battery pack should have. And out of this, now can we calculate the capacity?
90 AH.
So it is the V into C, that is the 36,000 divided by 400, that is 90 AH, right?
Yes.
So our pack sizing which is 400 volt, 90 AH. Now, what is the configuration? If it is the 3.7 volt, 3 AH of a pack we have, 3H cell we have.
400 by 3.7 is 108. So 108 and then 30 in parallel. So 108 S and 30P.
So this is the battery pack that we will require. And how much the power it can deliver to us?
Continuous discharge is 1C.
Yeah.
So 400 into 90, around 36 kilowatt it can deliver in
So
sustainably. And
standard it is V into I, right?
yes,
So voltage is 400 into 30. Sorry, it is 90, right?
yeah, 90.
So 36 kilowatt of a standard continuously power. That's what we can get out of this battery pack. And for a 10 seconds pulse, we can get the 3 times of it. So 108 kilowatt power. That's what also possible.
But how you have arrived 36,000? I can't get that.
36,000 for the energy or what?
Yeah, 36,000 watt hour per kilometer. What you have mentioned.
It is 108 is the total watt hour per kilometer is the requirement. For 300 kilometers, it is 300 into 108.
Okay.
And our efficiency is 0.9, so that has to be divided. So that gives you 36,000.
Okay.
So
okay, not considered the set WH. Overlook that. Okay.
now is it clear, the things?
Yeah. Actually, I have the not considered this 8 WH per kilometer.
Okay, 8 you have not considered. Okay, so this is for the four-wheelers. So this is always been provided by the powertrain engineer, and this is also the standard values. Actually, it is the estimations we do, but for each of the country, actually, there is a drive cycle method. There is a standard drive cycle method is there. That drive cycle method tells that if you have this rating of a vehicle, so how much of a power this motor or powertrain should take in this terrain. Like if it is a flat terrain where there is in the field regions, so this is the amount of power it should take for 1 kilometer. If it is the hilly region you are traveling, so how much the powertrain should take. So that is considered under the drive cycle. And for each of the country, largely it is for like India, if in case of a EV, for European countries or for the USA countries, it is defined. For the Africa and all, these are not defined yet, and even for the Latin America. And similar is the method that is defined for the petrol and diesel engine vehicles also. So how much the power that it should deliver, the engine should deliver for the working. So this is the drive cycle is being considered as the base one, and out of which we do the estimations of a powertrain taking the power for getting the propulsion or for the auxiliary loads, and then we average out those values, and this is the base factor used for the calculation of the battery pack. So as a battery pack engineer, this data will always be provided from the powertrain designer side to you. Okay, so this is the sizing for the EV applications we do. And then we have load applications like home load applications we are doing. So here is a two number of 60 watt for solar or backup energy application we are considering. So we have two number of fans of a 60 watt where the power factor is a 0.8. We have 200 watt of computer, that is also power factor 0.8. And there are the two tube lights of a 30 watt. Once we are deciding the power backup, so further load expansion approximately of a 20% of a extra load expansion, that's what we are considering. The efficiencies of our inverter is of 80%. We want the backup for 2 hours. The bank voltage is 24 volt. This is the battery voltage that we require is of a 24 volt. The wires would be connected and thereafter the wiring losses would be there. So we are considering the wiring losses, that is the loss factor would be of a 20%. The battery efficiency is considered here as a 90% charge and discharge efficiency. And there is a 20% is considered as the aging factor, the 100 to 80, the difference. The depth of discharge is 50%. So in this case, if the SOC dips down below of a 50% of a level, it should start charging in the inverter. And the operating temperature is kept at a 46 degree centigrade. Now for this application, we need to do a sizing. So first we calculate the total of a load. So our load would be two number of fans will be 120 watt. And the VA, if you will calculate, so you have to divide it by with the power factor. So that is the 150 VA. Compute load would be 200 watt and 250 VA. Tube light load would be 60 watt and 75 VA. Total electrical load in terms of a watt is 380, and total electrical load in terms of a VA would be 475 VA. Till this is clear, there is a no, this is the common thing that we do.
Yeah.
Now it comes about the inverter sizing. So size of our inverter is dependent on the how much the load on inverter has plus the extra expansion factor. That's what we are adding upon the efficiency. So the formula would become total load plus 1 plus AF upon the efficiency, and size of inverter comes to be 712 VA.
Yeah.
It is clear, right?
Yeah.
Now sizing of the inverter we have done. Now it is the load on the how much the load on the battery bank will come. So total of a load, and this will be multiplied by the how much the backup that you require in terms of the hours upon the voltage. That would be the total load factor.
Okay.
So, and that would be the amp hour actually. So total load is how much? It is watt is 380 watt into 2 hours of a backup that we require. So total of a 380 to 2, that's what is the capacity in terms of the watt. That's what you require. It means 380 watt of capacities that is required over here for the running of the application, and this amount of wattage we require for 2 hours. So that's why it is multiplied with your backup capacity, and your battery bank volt is 24. So that's why 24 we are dividing, and total of a load of your battery bank on the battery bank comes as a 32.66 amp hour. Now there is a temperature correction factor. So the temperature correction factor for the different of the battery packs. So I just give you a reference that this varies from 0.88 to 1.19. This is the value is. I'll find somewhere table and maybe I will upload the table. But this is the based on the temperature. There is the access or the there is a change in the pattern on the discharge of a current. I think we have seen the correlation earlier that if there is a temperature is quite higher or quite low, so there is a change in the pattern of the discharge, and if the temperature is near the room temperature level, so the exact amount of a discharge what you are expecting that will happen, and you will be able to use the maximum of the capacity. So 46, that's what is maybe for the LFP pack I'm talking about here. So for LFP pack till 50 degrees centigrade, the temperature coefficient factor is 1, where you can use the maximum of its capacity. Now, beyond of a 50 degree centigrade, like 70, 80 degree centigrade, if you have kept, so the temperature coefficient factor will increase. It will go up to like a 1.19 side. And if the voltage is depleting down, so it will come, if the temperature is depleting down, so the temperature coefficient factor can be dropped down to even 0.88 values. So, but at a normal of a temperature, normal room temperature levels, it is considered as a 1. So that's why temperature correction factor is a 1 that is considered. Size of your battery bank will be load into 1 plus the loss factor into 1 plus aging factor into the temperature correction factor. That would be divided by the N into DOD, the efficiency into DOD. So putting all the values into this, the size of your battery bank comes to be of a 101 Ah 24 volt. Now, if it is a maybe 3.2 volt and 6 Ah of a capacity of a cells we are using, so the configuration would be how much?
Around 8 series and how much?
7.5 it comes.
Yeah, 7.5, but 8 we have to consider.
Yeah. So it would be the, now here the if we will be lowering it, like if we are bringing it towards the 7 side, so our range is very small, it will be, and that will lead to the loss of the potential of the battery pack. So that's why at this level we will be selecting the higher side, that is the 8, because 7.5 series is not possible. We will be selecting as a 8. And the capacity would be how much? 101
6
divided by 6. That is 6.88.
Yeah.
So maybe 17. So 8S 17P.
Okay.
We have our configuration. Okay, so this was it.
So where these formulas are mentioned, size of the battery bank, this aging factor multiplied by factor.
These formula are mentioned, means I didn't get. In
Yes,
reference book that you are asking for?
Yeah, any reference for this?
I think reference I will have, maybe I'll share reference, but it is it is dependent on the derivations actually, all these formula.
Okay.
Reference also I have, but like the loss factor you need to multiply. The aging factor you need to multiply, only then the total of a load that could be calculated. I think this is the derivation you are asking for.
Yeah, 1 plus 1 plus they have mentioned. That's why I just ask. 1 plus.
Okay, I'll share you the reference I have. I will share you. Okay, so so calculations is still this, yes. Next part of it we will be covering in next of a session, where we will have a discussions on the, yeah, there is one more thing. I think there is battery sheet is there. Okay, so I will also upload you this battery pack calculation sheet. It is there for the cylindrical and prismatic cells both. So you can see over here, there are the green color and the this maroon colors are there. So in the green color, you can feed in your values. Green color cells, you can feed in your values, and the outputs will be generated in your the gray maroon color shades. So like the input, you want to, like you are in a field and you have to suggest anyone that what is the battery pack capacity he requires. So all the calculations you are not going to do. For the EV, this is specifically. So you will feed the what is the nominal cell voltage and capacity he has, what is the internal resistance of the cell is, what he is going to use, what is the peak discharge rate, what is the average continuous discharge rate of the cell is, what is the charging current rate, what is the maximum charging current rate, and up to what voltage you want to charge, like floating voltage, you want to keep it at a 4.0 or 4.1 something, and what is the cutoff voltage, that's what he is expecting. Thereafter, the mechanical characteristics like the length, width, height of the cell, what is the mass of the cell, all these things that you need to feed in. Thereafter, respective to the application, what is the primary requirement of the load, that is per kilometer watt hour requirement, what is the power requirement per kilometer for the auxiliary load, what is the application voltage requirement is, how much kilometers the vehicle needs to be, what is the range of the vehicle, that's what is expected, what is the efficiency is, that will be always be lesser than 1.9 is the maximum that is generally considered. Once we are charging, so what is the maximum of a charging, up to what level we are going, and what is the DOD, that's what we will be maintaining. So these are the input values of this will be, and based on which it will be giving you the data on the energy, what should be the charge current, what should be the discharge current, so that you can plan about the chargers also. What is the recommended charging, it should be there. Then how much the powertrain requirement wattage will be there, and based on which what would be the total energy requirement of the battery pack, what is the voltage, what should be the pack capacity, how many number of cells in the series, how many number of cells in the parallel would be there, what is the pack number of cells will be there, what would be the volume of your pack, like in the dimensions, how much the mass of your pack will become, how much the total battery pack mass would be, what is the maximum charge and discharge current of your battery pack, how much the power that you can take. So all these data that we will calculate it, and thereafter the thermal considerations are also there. So how much the heat this pack will be generating at a continuous discharge, how much the energy loss from the pack that will happen, and if you are not doing any kind of a thermal management method, how much the energy the pack will lose due to the heat. So all these things that this sheet will give you the calculation. So this is a ready reference sheet you can use for any of quick calculations.
So this efficiency of the powertrain is defined on which basis? What is the logic behind this 0.8? Is there any measurement?
It is the powertrain, actually that is the wrong term. It is the efficiency of the powertrain is yeah. So it is the how much the power, how much the current that you are delivering, how much the energy that is taking in of your powertrain, ratio to what, how much it is consuming. Means there is a in and there is an out is there, no? Means it's getting consumed inside of the motor. So the ratio that gives the efficiency. There is a transmission loss actually is there. So that's what it's.
Okay, but this is in the ideal condition, no?
0.9 is the ideal condition actually.
Okay.
And that's
because
what
this efficiency Means the tractive, if it is tractive load, then it will be different in case of stiffness. It may be when the vehicle is going on the slope. So this efficiency may vary, or
If the vehicle is going on a slope, yes, this efficiency will drop down.
okay.
So the more of a energy that you will require.
So this efficiency, which is in general considered as a plain road, and
That's why the
based
drive
on-
cycle concept is there. So
Okay.
like drive cycle concept that takes a consideration of a 5 degree of a inclination maximum. That's what you can maybe like a plain region you are traveling, but there is a this thing flyover is there. So there will be an inclination.
Okay.
That inclination will be continuously at a 5 degree of angle. So up to what the drive cycle is there. But if it is a continuously hilly region you are traveling, so there the efficiency would be dropped. You need the more of a power, and for which there is a separate powertrain would be required. It is not the common powertrain for each of the region.
Okay.
And that's what the region that in the hilly terrains the EV has not been successful yet.
Okay. Okay.
Okay, so we are keeping this till today. Tomorrow we'll be talking about the electrical design further.
Okay.
Vyom, any question?
No, sir, not right now. Thank you.
Okay. Okay, good night.
Good night.
Yeah, good night.
Okay, I will upload all these things for your reference so you can see it.
Okay.